In the world of computing, operating systems stand as the foundational layer that makes it possible to manage hardware resources and run application software efficiently. Understanding how operating systems work and how they have evolved into today's Unix-Linux family provides valuable insight into why we interact with computers in the ways we do. In this narrated piece, we shall explore the definition and purpose of an operating system, outline the historical background of Unix and Linux, examine the structural components of Unix-like systems, and finally introduce the Bash shell, a key command line environment. By examining these elements in detail, you will acquire a strong grounding for more advanced topics in system usage and administration. An operating system, or OS, can be described as the fundamental software managing the allocation of hardware resources and providing essential services to application programs. Without an operating system, individual programs would each have to handle tasks like memory allocation, CPU scheduling, and device access from scratch, causing not only a duplication of effort but also a high risk of conflicts. Consequently, the operating system serves as a centralized, efficient, and secure manager of the machine's core functions. A hallmark feature of any operating system is its role as an intermediary between the users and the computer's underlying hardware. When a user issues a command, whether through a graphical interface or a text-based console, the operating system decides which hardware components are needed, how data is read or written, and how the results are displayed. The operating system shields the user from the complexities of the hardware, offering a higher-level, more convenient model of computation. This arrangement ensures that software developers can write applications that run reliably across different hardware setups, provided they share the same operating system. Most operating systems include two main components: kernel. At the heart of the system lies the kernel, which loads into memory upon system startup. It is responsible for crucial responsibilities such as process scheduling, memory management, handling input and output, and enforcing access control. System programs. These are utility programs and libraries that assist the kernel's operation and provide services to user-level applications. They can include compilers, device administration tools, system monitors, and more. And one of the operating system's most critical jobs is to manage finite machine resources, like CPU time, memory space, disk storage, and peripherals, so that each process or program has fair and safe access. Now, this is no trivial feat. The operating system must keep track of what portion of main memory is allocated, which processes are in line for the CPU, and how data from disk or network should be queued. Effective resource management also ensures that no single program can monopolize the system, disrupting the performance or stability of the computer. The way in which the user interacts with the system is another foundational aspect of an operating system. Broadly, this is split into two categories: graphical user interfaces, or GUIs, and command line interfaces, or CLIs. GUIs provide windows, icons, menus, and other elements that allow intuitive interaction. A well-known example is the interface found in macOS. On the other hand, the command line interface is a text-based environment where commands are typed and executed. Unix-like systems, for instance, have a long tradition of relying on powerful shell environments, which we will discuss shortly. Most modern systems offer both approaches, though this course places greater emphasis on the command line given its power and flexibility in automating tasks and controlling the system at a granular level. Linux owes much of its character to the Unix tradition, a lineage dating back to the late 1960s. By examining the historical context of Unix and how Linux emerged, we can see why these systems emphasize certain core principles, such as textual configuration files, strong portability, and a modular design. Developed at Bell Labs, the original Unix quickly gained traction in academic circles, mainly because it shipped with its source code intact. Students and researchers could modify, learn from, and improve the system, fostering a widespread culture of collaboration. Over time, commercial variants of Unix appeared, offered by different companies. leading to variations in features and portability. When Unix became more proprietary, Richard Stallman launched the GNU project in 1983, aiming to build a completely free Unix-style operating system. The GNU project created essential utilities, like compilers, editors, and shells, but was missing a central kernel to tie it all together. In 1991, Linus Torvalds, then a Finnish university student, released an initial version of a Unix-like kernel he called Linux. Because it was free to modify and combine with the GNU components, a powerful open operating system formed. This was the genesis of the GNU Linux ecosystem, which thousands of developers around the globe enhance and maintain. Over time, Linux's kernel matured, offering robust support for diverse hardware architectures, while distributions packaged the kernel together with a wealth of software to present a complete system. A hallmark of Unix-like systems is the principle that everything is a file. Under this paradigm, disks, directories, devices, and even inter-process communication channels appear in the file system hierarchy. This design creates uniformity and reduces conceptual overhead. In addition, the system encourages modularity. Each small utility has one primary function, and more complex behaviors emerge by chaining these utilities together via the shell. The emphasis on portability, largely due to the C programming language, has allowed Linux to thrive on an array of devices, from massive servers to tiny embedded boards. Finally, the preference for transparency means system configuration often resides in readable text files, making it easier for administrators to audit or modify system behavior. Because Linux is open and flexible, many different distributions exist, each bundling the kernel with system libraries, installation frameworks, package managers, and user applications. Examples include Red Hat, SUSE, Fedora, Debian, Slackware, and Ubuntu. Some distributions target enterprise-grade reliability, while others focus on ease of use, minimal memory footprint, or dedicated server roles. In this course, we use Ubuntu 24 LTS, or long-term support specifically, taking advantage of its stable release cycle and extensive support from the Ubuntu community. Within any Unix-like operating system, the kernel is the undisputed core component. It is responsible for process management, scheduling which process runs on which CPU core and for how long to ensure multitasking is fair and efficient. Memory management, tracking which portions of memory are allocated or free and handling virtual memory mappings for each process. Device drivers, managing hardware devices from hard drives to network adapters through driver modules that interface with the kernel. And system calls, offering an interface through which user space programs request kernel-level services, such as reading data from a file or creating a new process. As soon as you power on a computer, the kernel loads into main memory. From then on, every application runs in conjunction with the kernel's oversight. When we talk about user interaction in a textual environment, we focus on the shell, a command interpreter that processes textual commands. You see, while the kernel runs at the heart of the system, the shell is effectively its face in the CLI world. You type in commands, the shell interprets them, and the kernel is called upon to perform the necessary tasks. Many different shells exist: Bash, Zsh, Fish, Tiash, and so forth. But Bash remains one of the most widely used, particularly in Linux distributions. Modern operating systems employ protection rings or modes, with Linux distinguishing between kernel mode, often called supervisor mode, and user mode, which is non-privileged. In kernel mode, the operating system can interact directly with hardware, while in user mode, applications must rely on system calls for privileged tasks. This separation achieves greater stability and security, preventing ordinary applications from circumventing the system's rules or overwriting memory they do not own. In kernel mode, there is full access to hardware resources and memory. Critical components of the operating system run here. However, if a kernel error occurs, it can crash the entire machine. In user mode, general applications or services operate here, constrained by memory protection mechanisms. Programs in user mode cannot read or write memory in use by other processes or by the kernel. Given the crucial role of the shell in Unix-like environments, it is worth taking a more detailed look at Bash, short for Born Again Shell. It evolved from the original Bourne shell, or sh, and includes numerous enhancements, making it powerful for both interactive use and scripting. Bash stands as the default shell on most Linux distributions, including Ubuntu. Besides simple command execution, it offers features like, command history and tab completion for efficient typing, variables that can store data or environment configurations, command substitution, and redirection to root input and output, conditionals, loops, and functions for creating advanced shell scripts. With Bash, you can chain multiple commands in a pipeline, redirect output into files, or even incorporate complex logic to build entire programs without leaving the command line environment. The shell can be seen as an orchestrator. When you type, for example, lsl/home, the shell interprets your input, locates the ls executable, usually in /bin or /usr/bin, passes l and /home as arguments, and waits for the command to finish. If you use features like pipes, such as lsl/home grep user, the shell sets up a unidirectional data flow between ls and grep, letting them communicate with each other without manual intervention. Moreover, the shell itself contains built-in commands like cd to change directories. It also often manages background tasks and job control, ensuring that you can suspend, resume, or terminate processes directly from the command line. Because we are focusing on the CLI, it is helpful to note its conventions. Command name, typically the program or built-in feature being invoked, such as echo or pwd arguments. These are additional parameters or data passed to the command. For example, echo hello world has echo as the command with hello world as the argument, options or flags. These are special arguments that tweak command behavior, often prefixed with a single dash like L or two dashes, such as help. The shell indicates its readiness for a new command by displaying a prompt. This is often marked by a $sign for regular users and a hash symbol for the superuser or root. On Ubuntu, you might even see a prompt that includes your username, the hostname, and your current directory. Once you press enter, the shell executes the command. It runs the program, collects any output to display on the screen, and then, it returns control back to you once the process is complete. When you turn on your computer and boot into a Linux distribution like Ubuntu 24 LTS, the kernel is the very first thing to load into memory. After that, system programs kick into gear, starting up all the services needed for hardware, networking, and other essential tasks. Eventually, you might log in through a graphical interface or perhaps open a terminal window to access the CLI. Every command you type there is passed by Bash, which coordinates with the kernel. It handles scheduling processes, allocating memory, and even reading or writing from devices as needed. This synergy of kernel-level resource management, user-friendly system programs, and a powerful shell environment exemplifies the Unix-Linux philosophy. Everything is a file. Regardless of whether you are dealing with data on disk, a hardware device, or a communication channel, the operating system treats them uniformly. Modularity. Most tasks can be tackled by combining smaller, dedicated utilities through the shell. Portability. The reliance on C and an open ecosystem means you find Unix-like systems on everything from embedded controllers to massive servers. Transparency. System configurations remain accessible through text files, and you can examine or adjust them without opaque binary layers. Throughout this segment, we have defined what an operating system is and explored how it mediates between hardware resources and user-level applications. We've charted the historical rise of Unix and how Linux emerged as an open, community-driven kernel, uniting with GNU components to form fully featured operating systems. We've also highlighted fundamental Unix-Linux structures, from the kernel's privileged position managing processes and memory, to the shell's role as an interpreter in user space. And finally, we provided an overview of Bash, a command-line environment that exemplifies the power of the Unix approach to system interaction. The crucial takeaway is that by learning to navigate Linux at the command line and by understanding the operating system's essential components, you gain direct insight into how your system allocates resources, launches programs, and organizes data. This knowledge not only empowers you to solve problems more efficiently, but also lays the groundwork for advanced topics like system administration, scripting, and deeper programming approaches. Thank you for engaging with this overview of operating system fundamentals, the historical context of Unix at Linux, the structural layout of a typical Unix-like system, and the pivotal role of the bash shell. By solidifying these core concepts, you will be well prepared for deeper explorations of process management, shell scripting, networking, security, and the many other facets that make Linux an enduring and vibrant platform.